You have seen the videos showing robotic hands that move with uncanny fluidity, and you are right to be impressed. Those demonstrations represent a genuine leap in capability, yet they mask a fundamental engineering crisis. The gap between these high-fidelity prototypes and the robots working on factory floors today is defined by a brutal trade-off between sensor latency, actuator torque, and material compliance. By the end of this explanation, you will understand why achieving true human-level dexterity requires abandoning the human hand design entirely. Consider the recent breakthroughs in sensorized soft skin and the BiDexHand, a system boasting 16 degrees of freedom. These designs integrate tactile sensing directly into the finger surfaces, allowing the robot to distinguish between a fragile egg and a rough stone without visual confirmation. This fusion of touch and proprioception bridges the gap between what the robot sees and what it feels. When a robot learns to reorient an object in its palm, it is not just following a pre-programmed path. It is using AI-driven frameworks to adapt to novel objects in real time. These systems can load dishwashers or handle delicate electronics with a precision that was impossible just a few years ago. However, there is a critical constraint hidden within this progress. Every additional degree of freedom adds complexity to the control loop. As you increase the number of joints, you inevitably increase the latency between sensing a slip and applying corrective torque. If the system lags by even a few milliseconds, the object slips. This is the first major bottleneck. You cannot simply add more sensors and motors and expect linear improvement. The physics of the materials themselves impose a limit. Soft skins provide the necessary compliance to grip fragile items, but they introduce hysteresis and non-linear behavior that makes precise force control incredibly difficult. Now consider the role of artificial intelligence in solving this. Robot learning frameworks are evolving to overcome the limits of random exploration. Instead of trying millions of random movements, these systems use imitation learning to master complex tasks. They watch human demonstrations and translate those movements into motor commands. This allows them to handle objects they have never seen before. But here is the catch. The hardware must be able to execute those commands fast enough. If the actuator torque is too low, the fingers cannot generate the necessary grip force. If the torque is too high, the soft skin deforms unpredictably. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This brings us to the central tension in the field. We have designs like the ISyHand, which features an articulated palm and multiple fingers, pushing the boundaries of biomimetic complexity. These systems achieve human-like manipulation by mimicking the anatomy of the human hand. But is this the optimal path? There is a growing body of research suggesting that human-level dexterity relies more on wrist flexibility and finger abduction than on the sheer count of fingers. The human hand is not a perfect machine. It is a biological compromise shaped by evolution, not by engineering optimization. Evidence from major robotics challenges reveals a surprising truth. Simpler, non-anthropomorphic designs often outperform complex human mimics in practical applications. A specialized gripper designed for a specific task can be faster, more reliable, and cheaper than a five-fingered hand trying to do everything. The debate is no longer about whether we can build a hand that looks like ours. The debate is whether we should. The current consensus is shifting away from the idea that we must copy the human form to achieve human-level performance. This is where the knowledge gap becomes most apparent. While sensorization and learning algorithms are rapidly advancing, the field lacks consensus on the future of dexterity. We are pouring resources into perfecting the human hand, yet we have no data proving that this is the most efficient route. Some researchers argue that we should abandon the anthropomorphic design entirely. They propose configurations that prioritize task-specific efficiency over biological mimicry. A hand with two opposing fingers might be better for a warehouse than a hand with 5 fingers and a thumb. The integration of sensorized soft skins remains a key trend, providing the tactile feedback necessary for handling fragile objects. But the real innovation is not in the skin itself. It is in the realization that the skin is only useful if the underlying actuation can respond quickly enough. The latency between the sensor and the motor is the enemy of dexterity. As we push for higher degrees of freedom, we are pushing against the physical limits of current materials and control architectures. Here is the thing that changes everything. The next level of dexterity will likely not come from making the hand more human. It will come from making the hand more specialized. Open source initiatives like BiDexHand are accelerating innovation by democratizing access to high-performance designs. This allows for rapid iteration and community-driven improvements. But the ultimate breakthrough will require us to stop asking how we can make a robot hand work like a human hand. We must start asking what the ideal hand looks like for the specific task at hand. The future of robotics is not about building a better copy of us. It is about building tools that are superior to us in their specific domain. We need to accept that the human hand is just one solution among many. The most dexterous robot of the future might look nothing like a hand at all. It might be a multi-fingered configuration optimized for assembly, or a soft, compliant gripper designed for food handling. The key is to let the task define the design, not the other way around. This shift in perspective is the most valuable insight we can take away. We have spent decades trying to replicate the human form, but the data suggests that the most efficient path forward lies in breaking free from that constraint. By focusing on the specific trade-offs of latency, torque, and compliance, we can design systems that outperform the biological standard. The next generation of robotic hands will not be defined by how many fingers they have. They will be defined by how well they solve the problems we give them. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.